Hello, everyone. Thank you for coming to this webinar. My name is Yan Yao. I'm a professor of electrical and computer engineering department at the University of Houston. I'm also a PI of Texas Center for Superconductivity. I also appreciate Professor Ramana and Andres for the invitation. So recently, lithium-ion batteries and electric cars have been a huge hit in the news. You may also heard about Tesla's stock price skyrocket 7 times since beginning of this year, and the current market value over $600 billion. You may have also heard about a solid-state battery startup called QuantumScape went public last month and showcased their hit and home run technology earlier this week. So in today's webinar, let me remove the heat of the batteries, lay out the battery challenges we face today for both electric vehicle and stationary storage application. I will also show you the research we have done in my group to address these challenges. So to predict the batteries for the future, we need to look back at the history of batteries. So battery have over 220 years history since Volta invented the voltaic pile in 1799, who discovered electricity could come from chemical reactions. So this led to the birth of electric chemistry. So in 18th century, fuel cells, lead acid batteries, nickel cadmium batteries have been invented. All this battery using water as the electrolyte, and they show high rate, but the voltage is limited up to 2 volt. In the middle of 19th century, beta alumina as a ceramic has been discovered for sodium conductors. The Ford motor pioneered high temperature sodium sulfur batteries. So this is the first device using solid state electrolyte. Interestingly, what we hear most often is the lithium-ion batteries, a relatively young field. Research starting early 1970s on lithium metal, then intercalation cathodes were developed. Commercialization of lithium-ion batteries started in 1991. So in contrast to aqueous batteries, lithium-ion batteries using non-aqueous electrolyte that enable 4-volt batteries. So looking at this last 220 years, if you ask what is driving the battery technology development, the answer is the energy density. Energy density states how much energy you can store in total weight or in total volume. So lithium battery have 5 times higher energy density compared to that of lead acid batteries or nickel metal hydride batteries. Battery is a complex interdisciplinary research field, not only involving electric chemistry, knowledge on semiconductor, solid-state physics and chemistry, solid-state ionics are also important. So there are many scientists shown here contribute to the fundamental concept in battery research. Those highlighted in red received Nobel Prize related to batteries research. So excitingly, last year, a Nobel Prize in chemistry goes to 3 gentlemen for the development of lithium batteries. Jiang Goodenough demonstrated the first 4-volt cathode using lithium cobalt oxide. Later, lithium magnesium oxide and lithium phosphate were also discovered by him. So Jiang received the award at the age of 97. Stan Whittingham discovered the intercalation concept for rechargeable batteries in 1970s. Akira Yoshino developed the first prototype of lithium batteries in 1985. So then a commercialization of lithium batteries was developed by Sony and Asahi Kasei in 1991. So since the last 3 decades, we have witnessed the astonishing growth of lithium batteries that have fundamentally changed our lives. Last year, the lithium battery annual production reaches 300 gigawatt hour and is projected to surge to 2 terawatt hour scale in 2028, just based on electric vehicle market alone. So to get that number, a battery breakthrough is needed. So you may know Currently, every year, there's 100 million cars are sold every year. However, there's only 2% are electrified today. The reason for that 98% cars are not electrified are because today's batteries are not competitive with the internal combustion engine. More specifically, today's batteries does not have extremely high energy density, which limits the driving range. You also do not have the ability to charge a battery as quickly as you can refuel the gasoline engine vehicle. So in many cases, the batteries are expensive, therefore driving the cost above mainstream vehicles. In many cases, batteries doesn't last uh, long as the vehicle itself. So finally, the batteries are made of liquid electrolyte. These batteries, are using liquids which are hydrocarbons, which means they are fuels and raise safety concerns. So I believe the batteries that can address all these five limitations can narrow the gap with the combustion engine and dramatically increase the penetration to 98% of non-electric market. So that's why Bloomberg and New Energy Finance predict electric vehicle batteries would increase from 2 to over 550% in the next 20 years. So in addition to electrified transportation, transition from traditional centralized electric grid to decentralized smart grid, where clean energy and the Internet of Things play a significant role, is another big trend. So traditional grid are demand driven, have almost no storage capabilities. Storage of electricity by batteries could reduce the consequence of severe weather condition, improve the response of the grid, and make it less complicated. Station battery can make profit when the electric cost is low to charge the battery and sell the electricity to the grid when the price is high. So this requires the cost of battery to be less than 5 cents per kilowatt hour per cycle. However, today's batteries are too expensive to reach this target. So in many cases, the battery do not last 5,000 cycles. In today's batteries for the grid are also not safe enough. So imagine a device situation could happen when a megawatt hour scale battery catch fire. So it's clearly a battery for the electric grid should be designed differently from electric vehicle batteries because the cost, cycle life, and safety are higher priorities than energy density in this situation. So my group has been working on both lithium-ion and lithium metal batteries for high energy applications. We have developed a diagnostic platform for understanding cell failure mechanisms. We have also worked on developing new manufacturing process to reduce cost. For grid-scale storage, we work on multiple beyond lithium-ion battery chemistries. We focus on intrinsic safe and low-cost battery materials by choosing earth-abundant organic materials. We can also choose earth-abundant sodium and magnesium metals as anode. So in the rest of my talk, I will show you three examples. The first is a high-energy solid-state lithium battery. The second is a diagnostic platform. And finally, high-power magnesium batteries for the grid application. Let me start with the high-energy solid-state organic lithium batteries. What is solid-state lithium metal batteries? So I borrowed a slide from QuantumScape, a startup working on this field. So on the left is conventional lithium-ion batteries. You have a cathode and anode separated by a porous polymer separator. So the entire cell is flooded with a liquid electrolyte, which is a medium for lithium-ion to travel. In a solid-state lithium metal batteries, you can use the same cathode, but replace the porous polymer separator with a ceramic separator. You could use lithium metal as anode, or in the anode-free design, lithium metal could be plated during the initial charge process. Due to the reduced volume and the mass compared to that of lithium-ion batteries, lithium metal battery can potentially double the energy density from 250 to 500 watt-hour per kilogram. So this could enable a greater driving range, 15-minute fast charge, and a safer operation due to non-flammable electrolytes involved. However, there have been extremely difficult to do so, particularly plating and stripping lithium metal at such a high rate without any side reaction has been extremely challenging. I hope to see more details how QuantumScape was able to accomplish this in the future. The leading cathode material using all solid-state batteries are mainly nickel, magnesium, cobalt oxide, short for NMC. So even solid-state batteries can work well. The cost of battery would still be high due to the nickel and cobalt used in these cathodes. So to make cobalt-free and nickel-free cathodes and reduce the cost, we propose to using organic electrode materials, which are made of carbon, hydrogen, oxygen, without any transition metals. So organic compounds with well-understood redox active function groups can reversibly store and release multiple electrons and protons per molecule. So organic lithium batteries has the potential to deliver material level specific energy over 1,000 watt-hour per kg, place them in the same category as NMC lithium and lithium sulfide batteries. So Fang Hao was the first graduate student who worked on this project. He's now at the GM R&D Center. The organic we used in this research is called PTO, and each molecule undergoes 4 electron reduction along with 4 lithium ion insertion into the molecular crystals and coordinating with oxygen atoms. So the reaction corresponding to a theoretical capacity of 409 milliamp hour per gram. So the cathode composite was prepared by mixing PTO, LPS electrolyte, and carbon with a pestle motor mixing, followed by uniaxial powder compaction. So the PTO lithium cell exhibits a discharge voltage about 2.2 volt with a specific capacity about 320 milliamp hour per gram, corresponding to a material utilization of 78%. So the cell cycles stably at 0.3 C for the initial 200 cycles and maintains 61% of its maximum capacity over 1,000 cycles. So this is a truly remarkable capacity and stability for new cathode materials in solid-state batteries, which have been studied only recently. To understand the stability, the evolution of the cathode electrolyte interface was probed by in situ electrochemical impedance. The Warburg coefficient can be extracted from the electrochemical impedance spectra, which reflects ion diffusion resistance as a cathode electrolyte interface. What we see here is that the AW remains low during the majority of the cycle, but increases sharply when the voltage exceeds 2.9 volts versus the lithium, at which the potential oxidation of electrolyte is expected. So upon discharge, the AW quickly reverts to lower value and remains so until the charge to the high potential in the next cycle. So we note when NMC is used in solid-state cells, a thin oxide layer coating is necessary. Otherwise, we will see irreversible increase of individual resistance. So the fact that no coating layer is required for PTO is due to the moderate working potential, and thus which enables a longer cycle life for this battery design. To further improve materials utilization, we look into optimizing the microstructure of the electrode. So in contrast to NMC particles, which have uniform shape and size, organic typically have wide distribution of the shape and the size, making it very difficult to engineer the microstructure. So we discovered a cryo-milling process can greatly reduce the PTO domain size. From the cross-section SEM images, the black phase is a PTO with carbon, and the white phase are solid electrolyte phase. So we have therefore segmented the SEM images based on grayscale. We see the size of PTO domains for cryo samples is about a factor of 10 smaller than high-mu ones. Such significant reduction in the size of the active material contribute to the improved battery performance. Now the chromium sample reached the capacity of over 400 milliamp hour per gram, which is a mature utilization of over 99.5%. So this is the first time organic electron material accomplished full utilization in a ceramic electrolyte-based battery. So the material level specific energy also reached 828 watt-hour per kg. This is only the material level, not the full cell level. But nevertheless, this puts the organic, the best solid state chemistries and shows the potential for organic electron materials in enabling high energy batteries. The cycling performance of the chromium sample is also very good. At 0.3 C, maintains 100% of its maximum capacity after 100 cycles. However, one remaining key issue is the low mass fraction of PTO in the cathode, only about 20%. So Dr. Jibo Zhang took the challenge to increase PTO mass fraction. Jibo found while increasing the PTO fraction from 20 to 50%, specific capacity decreased quickly. This corresponding to utilization from 80% to 32%. So in other words, the capacity didn't scale with PTO ratio following this theoretical line, but reach a plateau and do not further increase. Jibo found the origin of this low utilization is due to the unfavorable microstructure. Electrolyte islands with size between 2 to 15 micrometer were surrounded by a sea of PTO and carbon mixture. Such a microstructure is unfavorable for lithium ion transport because electrolyte couldn't find the percolation network, and the PTO has a lower ionic conductivity for lithium ion transport. So the reason for forming such an undesired microstructure is related to the soft and compliant nature of organics. Organic deform easier before lithium ion solid electrolyte deforms. So to reverse this microstructure, we actually invented a solution process method that preforms a core shell structure particles, where the PTO core is surrounded by the electrolyte shell. So the deformation of PTO during the uniaxial pressing process could change the microstructure compared to the dry process. The cross-section of solution process composite at 40% active material shows that the phase separation is clearly reversed. Now the electrolyte domain forms a continuous network with the PTO domain embedded in between. This is in contrast with the dry process at the same PTO fraction. So although this is solution process, we have to dry the solvent off in the oven to make it fully solid state. We also did the top seams measurement. So images not only confirm that's more uniform spatial dissolution of PTO in the solution process compared to those in the dry process, also provide molecular information of the interface. So we find the green one related to the PTO is partially reduced to form lithium X PTO, and also electrolyte is partially oxidized to polyphosphate sulfide. So solution process also result in slight increase in ionic conductivity and a 6 times increase in electronic conductivity, so leading to a balanced transport in the solution process sample. We note here, typically reactions between cathode and electrolyte is to be avoided or suppressed. For example, coating on MC particle oxide coating is used. However, here is an example showing the reaction between the cathode and electrolyte can be used for the benefit of forming a better microstructure. So as a result, the area capacity now scales with PTO mass fraction in this red line. In comparison, the dry process is a blue line. So the material utilization actually can go up to 98%, and cycling stability is excellent over 100 cycles. We also compare the specific energy considering the total cathode mass in this figure. So the value can reach 300 watt-hour per kg, which is on par with inorganic cathode, such as lithium cobalt oxide, which has a lower capacity but a higher voltage. But we show better cycling is possible without NA coating applied. So this work shows our effort in using earth-abundant materials that potentially can lower the cost and reduce the reliance on any metals. There are also still many challenges to overcome, such as low density of organics, or reduce the electrolyte thickness to less than 50 micrometer to improve the volumetric energy density and rate performance. So that's the first example. So in addition to the new material discovery for solid-state batteries, our group is also working on a diagnostic platform for better understanding of cell failures and mechanisms. So UH and RISE form a collaborative team to approach the complex origin of battery failures. This work is funded by DOE VTO office. So the failure mechanism of a solid-state lithium battery may be briefly attributed to two main causes. One is the interfacial resistance increase, and second is about lithium dendrite growth. So the resistance increase may be attributed to electrolyte decomposition at the interface void formation, so which happens at both cathode electrolyte and anode electrolyte interfaces. So we decide to approach this complex origin of battery failure using not only one technique, but a combination of three techniques as a tool set, including the time of flight SIMS measurement for chemical analysis. We will use FIB 3D reconstruction inside the SEM for structural analysis. We are also using in SEM nanoindentation for mechanical analysis. The operando characterization requires transferring a cell between the instruments without exposing to the air. So therefore, we first developed an air-free transfer vessel. At the heart of the vessel sits a cell test platform, which is equipped with a microcell mount, where electrochemical tests can be performed in situ. Heating and pressure sensing module are also integrated in this platform. This slide shows an example of SEM observation of a cross-section of the thin cell mounted on the platform. The SEM shows a cross-section of tri-layer structure of cathode, NMC, and the lithium electrolyte, and this electron layer and this anode lithium indium layers. So we can also perform the Raman spectroscopy on the same thin cell and the same area. So that test platform has been also optimized to deliver performance similar to non-micro cells. The first discharge capacity reached 200 milliamp per gram, which is comparable to that thin cells. So the pressure change can also be monitored in situ. So this results indicating the efficacy of the vessel in isolating the test platform from ambient condition without interfering any analytical beams. So for mechanical characterization, a similar transfer vessel containing a nano-indentator has also been developed. So this image showing the vessel inside the SEM opens the cover, can expose the tool we used for mechanical measurement. So this is a Histron nano-indentator. So special result mechanical test can be performed by locating the diamond tip at different locations. So when this shows that when the tip is located for lithium cobalt oxide particle, we can extract the modules and hardness for the lithium cobalt oxide. So if the tip intends electrolyte area, we will also see the measurement of the modules of electrolytes 1 order of magnitude smaller. So in situ, in SEM nanoindentation has high spatial resolution to probe the heterogeneous composite cathode in this case. to separate, differentiate the cathode versus electrolyte, and even to measure the mechanics of the interface. So finally, we also equipped with a focused ion beam SEM using slice and view function. They can enable a reconstruction of the cathode composite. In this example is a PTO LPS freeze mill sample. We can resolve the network of electrolyte. This is the PTO cathode, and we can also see the pores connectivity structure in the cathode composite. So segmentation of the 3D images provides information such as volume fraction and the tortuosity. And also we can see the pores in this cathode composite is less than 1%. So in summary, this work is to develop a platform for structure, chemical, and mechanical characterization in solid-state lithium batteries. The in-depth understanding allows us to effectively predict and optimize the physical and chemical properties during the charging and discharge process. Now we have discussed lithium metal batteries. Let's switch the topic to magnesium metal batteries for grid-scale energy storage. So there's a need for grid-scale energy storage becomes more and more pressing. We have sought to less expensive and more readily available element alternative to lithium metal. So magnesium is among the top 10 most abundant elements in the Earth's crust. Compared to lithium, here at least 2 orders of magnitude higher than that of lithium. So in our recent review published in Nature Energy, we reviewed the current status of the multivalent metals, ion battery research, and provided a roadmap for future development. So among many metals such as magnesium, calcium, zinc, and aluminum, magnesium battery is considered one of the prime candidates. The direct use of magnesium metals as anode is important. Magnesium metal has a reputation of dendrite-free plating as a compact crystals. So this is in sharp contrast with lithium metal growth behaviors. However, recent years, reports have shown magnesium also forms dendrite when the electrolyte is not fully optimized to have highest cooling efficiency. So a major challenges for magnesium battery is the lack of efficient cathode material. So magnesium ions have twice the charge of lithium, while they have similar ionic radius. So magnesium cations are more polarizing than lithium. So as a result, magnesium dissolution from electrolyte solvent or dissolution with its ions need to overcome a huge energy barrier like this. Furthermore, after this dissolution or dissociation, the integration into the cathode also needs to overcome a high energy barrier because of strong primitive interactions. So there are two approaches to address these challenges. The one is the cycle the battery at the elevated temperature. For example, 60 degrees C, Doran Alvarez group have shown that shower phase can reach theoretical capacity. So the other approach is to storing magnesium ions in its complex form, such as using DME molecules solvated magnesium ions. So both approaches have disadvantages because elevated temperature would require a heater, which is not very practical. Storing complex ions would lead to a limited cycle life caused by volume change due to cold insertion of the bulky solvent molecules. So therefore, the cathode materials require a new reaction mechanism to support fast magnesium 2+ storage. In our recent work, we have demonstrated heterogeneous ionization redox cathode chemistry to circumvent the ionic dissolution and solid-state diffusion challenges. PTO was again selected as a model compound due to its high theoretical capacity and solvent-free magnesium storage. So the voltage profile consists of 2 plateaus, each corresponding to 2 electron reactions. The average discharge voltage is about 2 volt, and the capacity is about 315 milliamp hour per gram. Both of these values represent one of the highest value for magnesium batteries. So we probed the cathode reaction mechanism using UV visible spectroscopy. The reduction of PTO in the magnesium electrolyte actually is a heterogeneous liquid-solid reaction. We use a switch lock cell and we discharge to different DOD and then dilute the reaction electrolyte with DME. What we see is that the PTO is reduced to soluble magnesium 1 PTO intermediate and then to insoluble Mg2 PTO. So the precipitation of Mg2 PTO is a spontaneous process that overcomes the solvent stripping from magnesium. Look at the chemical reaction. PTO reduction involves no covalent bond breaking process. So that's why the reaction is intrinsically very fast, because there's no bond cleavage or reformation in the cathode. Here we show that PTO electrode at the very C rate. At the 5C, the power is 3 kilowatt per kilogram, surpassing the state-of-the-art magnesium batteries. So this is a new class of redox chemistry which bypasses the need of solid-state diffusion while solely storing magnesium instead of its complex ion kind of forms. Like other liquid-solid reaction-based batteries, soluble reaction intermediates bring two major concerns. First is a cathode mass loss caused by continuous dissolution. And second is that dissolved species will diffuse to the anode side and cause passivation of the metal anode. So both of these issues were controlled effectively in our system. The first, solubility of magnesium 1 PTO actually is less than 1 millimolar. So this is 100 times less than that of polysulfide. Dissolution of PTO is suppressed by inserting 2 micrometer thin lightweight graphene oxide membrane between the cathode and the separator to trap the magnesium 1 PTO intermediate, but still maintain electric contact because this graphene oxide membrane is electronic conductive. So all the capacity trapped by the Mg1 PTO can still contribute the capacity of the cathode. So this concept is borrowed from lithium sulfur battery and has been proved very effective. The battery has an initial activation step due to the high viscosity of G4 electrolyte. Then it becomes stable for 500 cycles with a capacity retention over 84%. So on the second question about magnesium surface passivation, we test magnesium plating in G4 solution with and without magnesium 1 PTO. We see there's no variation in the overall potential in the plating and the streaming process, indicating there's also minimum change on the mantle in the PTO cell. However, in comparison, when magnesium sulfur reaction, the intermediate, we can see the overpotential has almost been doubled. So this probably is related to much higher solubility of the intermediate reaction in Mg sulfur process. While the fast kinetics has been shown earlier, the cell power is still limited by the mass transport in the MMC G4 electrolyte. So Rana and Oscar from Toyota tried a variety of solvent blend and found several mixture solvent provide much better solubility. Here we use DME and G2 as a mixture, which provides a best solubility, reaching ionic conductivity of 6-fold increase. So we have observed a mixed solvent shell of magnesium from NMR studies here. So cyclophotometry shows a 99.9% Coulombic efficiency, reaching impressive 100 milliamp per centimeter square. So this is 10 times higher than that of MMC G4 electrolyte. In asymmetric magnesium copper cells, even at the 50 milliamp per centimeter square, we still can reach a Coulombic efficiency about 99.7%. The morphology of magnesium plated on copper shows dense, smooth, and danger-free morphology. This is deposit at 20 milliamp per centimeter square for area capacity of 3 milliamp hour per centimeter square. So the smooth, we can also apply similar condition for symmetry cells over 5,000 minutes. The smooth voltage profile indicating effective mass transport in the electrolyte. So this results consolidate magnesium metal as a safe anode even under demanding conditions. So finally, we couple PTO cathode and new DME G2 electrolyte yield a high power magnesium battery prototype. We have shown at 20C and 50C, the capacity remain 200 and 210 can be retained. So stable cycling at the 5C can be maintained over 200 cycles. So the Ragone plot of state-of-art magnesium batteries store magnesium 2+ cations are summarized here. So intercalation cathode material, such as Chevron phase or spinel TS2, shows low power even at 60 degrees C. The conversion cathode, such as sulfur and iodine, display a slow kinetics up to 2C. So in this work, our cathode relying on ionization redox mechanism shows a power of 30 kilowatt per kilogram. So 2 order magnitude higher than the current highest. So in summary, this work developed a high power magnesium battery featuring organic quinone electrode and with a tailored boron cluster electrolyte. Future work needed to increase the PTO fraction and also lean electrolyte design. So, but this work sets a new direction for developing high performance magnesium batteries. So in this talk, I have reviewed the challenges of batteries for electric vehicles and grid-scale batteries. Energy density and fast charging are the key to the EV batteries, while cost and safety are more important considerations for grid-scale batteries. We have discussed 3 examples from my group, from lithium also to magnesium. So I didn't have time to touch upon aqueous batteries in my group and also sodium-ion batteries. So central theme of this work is to use low-cost organic materials as well as the intrinsic safe electrolyte. So let me end my talk by acknowledging the people who actually did the work, the wonderful students and postdocs in my group. Some of them have already become professors somewhere in the world. I was very fortunate to work with those talented students and postdocs. So I would also like to thank collaborators and funding agencies here. So with that, thank you for your attention. I would be happy to answer any questions.